So we have seen the meaning of a rank of a matrix and the inverse of the matrix in the last lecture. Today I will be talking about eigenvalues, eigenvectors of a matrix. Okay. And I want to emphasize that this is probably one of the most important areas of linear algebra to find eigenvalues and eigenvectors of matrices, and it is used in all branches of science and engineering. Okay. So, let us get to the discussion of eigenvalues and eigenvectors. In order to do this, we will restrict our discussion to square matrices only, and that is where eigenvalues and eigenvectors are defined. And in order to do this, we will just mention that it helps to think of a matrix in terms of operation on a vector. So, for example, you could have a matrix A and that operates on a vector x, okay, and when this matrix operates on a vector, it will give you another vector. So, I will just call that vector y. Okay. So, a matrix operates on a vector to give you another vector, and now we say what is the relation between x and y. Okay. What is the relation between x and y? Is there any relation between x and y? In general, x and y they can be completely different vectors. Okay. Now, so for a matrix, now we ask the question, is there some vector, I will call it x lambda, such that matrix A preserves the direction of x lambda. Okay. So, the question we are asking is there some vector x lambda such that the matrix A preserves the direction of x lambda? That means what we mean to ask is there a matrix, and I will use a different color for this because this is an important equation. So, is there a so for the same matrix A, when it acts on this particular vector x lambda, okay, it gives you something that is proportional to x lambda. It gives you a vector that is actually proportional, and this constant of proportionality I will call it as lambda. Okay. So, lambda is the constant of proportionality. This is a scalar or a real number. Real number if you are dealing with real matrices. Okay. Now, the question is we are saying that for any given matrix A, there can be certain vectors x lambda such that when A operates on x lambda, it gives a vector that is proportional to x lambda. So, in other words, this is proportional to x lambda. Okay. So if this is a case, then this equation is called an eigenvalue equation. This is refers to as an eigenvalue equation. And what we say is that x lambda is an eigenvector of A, of matrix A with eigenvalue lambda. Okay. It is very important to get the sense of this statement. What we mean is that x lambda is an eigenvector of the matrix A corresponding to the eigenvalue lambda. Okay. So, it is not that you cannot generally define eigenvectors and eigenvalues, you have to talk in reference to a particular matrix. Okay. And always for a given matrix there can be many eigenvectors and corresponding eigenvalues. So, it need not be unique. Okay. So, now how do we solve for eigenvalues? So, what we said is that we just mentioned that this equation is called the eigenvalue equation, and in general for a matrix there can be more than one eigenvalue. okay, then there can be more than one eigenvector, and we will just go ahead and try to see what you need to do to calculate the eigenvalues and eigenvectors. Okay. So, what we will do is we will start with this equation, we will write Ax equal to lambda x, and what we will say is that that implies A minus lambda times identity times x equal to 0 vector. Okay, so, what I did is I just took the lambda to the left, I multiplied it by identity so that I get a matrix, and this is A minus lambda I x equal to 0. So, it is the same as the above equation, I just rewrote it in a slightly different form, but the advantage of writing in this form is that now looks like a set of linear homogeneous equations. Okay, if you remember, this looks exactly like your set of linear equations where you had something like you know, Ax equal to B. We had, this was the general linear system that we had. Okay, now in this case what you have is something like Ax equal to 0. So, what we have is so this kind of equation is called a homogeneous equation. Okay, so you have some matrix A, instead of A I have A minus lambda I in this case, okay, but when it operates on x you get the 0 vector. That means my system of equations looks like this. So, if my A has the usual, if we use the explicit notation for A, then you have A11 and then you have minus lambda times I. So, identity matrix just has 1 along the diagonals. So, lambda times identity will just have lambda along the diagonals, and you are subtracting that from A. So, what you will get is you will get a subtraction of lambda from the diagonals, and the off diagonal elements will have no change. So, it will A12, A13 and so on up to A1n if it is an n by n matrix, and so on. So, you have A21, now we will have A22 minus lambda, A23, A2n and AN1, AN2, AN3, ANn minus lambda. Okay. So, this is a matrix, and what you have is this multiplied by x. X is a vector, I will just give it some coefficients x1, x2 up to xn, this equal to 0. I should explain what this 0 is. So, this is your 0 vector, which is basically a vector with all elements 0. It is an, so this is a column vector, n dimensional column vector, all elements are 0. This is an n dimensional column vector, that is your x. Okay. And this is a matrix where you have along the diagonals you have A11 minus lambda. What you are doing is you want to solve this set of equations. Okay. Now, the nice thing about this is a set of homogeneous equations. Okay. Now, in order for them to be consistent, and solution to exist, so in order for solution to exist, we must have determinant of this matrix, that is determinant of A minus lambda I, that is actually this matrix, this whole matrix. So, the determinant of this matrix should be equal to 0. Okay. Only if the determinant of this matrix equal to 0 can we have solutions of this problem. Okay. So, notice now we just come back to the eigenvalue equation for a minute, this equation, this eigenvalue equation. Now, what we are going to do is we are going to take this equation and solve for both x and lambda. When we solve for x and lambda, okay, with the same equation, okay, you are going to solve for both x and lambda. Now, when you set the determinant of A minus lambda I equal to 0, okay, then you will get a polynomial equation for lambda. So, this is a polynomial equation for lambda. And we will see an example of this in a minute. Okay. And you can see just by looking at the product along the diagonals, you can see that you will have lambda raised to n power coming in this determinant. So, this determinant will contain a term that has lambda raised to n. So, it is an nth order polynomial equation, okay, and in general you will have n roots. Okay. So, that means the number of eigenvalues is equal to the dimension of the matrix. Okay. So, you have n eigenvalues for this equation. Okay. So, now next is next is you want to take those eigenvalues and solve for the eigenvectors. Okay. So, as we said earlier, our goal is to determine both the eigenvalues and the eigenvectors. Okay. So, so corresponding to an eigenvalue lambda, okay, I should mention that here I have not put x lambda explicitly because I am using all these subscripts on x, okay, but if you want you can put an x lambda, okay, it is just a notation. Now, when you solve for the eigenvalue coefficients, how will you solve for these eigenvalue coefficients? So again you go back to our equation, you say you had a times x equal to lambda x, okay, and this implies a minus lambda I x equal to 0. Now, we choose one value of lambda and solve for corresponding x. What I mean is if you choose a value of lambda, then this determinant is this matrix A minus lambda I is well defined. So, you have A11 minus lambda, A13 and so on up to A1n, and A21, A22 minus lambda, A23, A2n, AN1, N2, N3, ANN minus lambda. This is your A minus lambda I, and then you have the coefficients of x, which I will have x1, x2 up to xn. These are the coefficients of the x vector, and this should be equal to 0. So to do is to solve for x1, x2 up to xn. Note that the determinant of this matrix equal to 0 implies, okay, these equations are actually dependent equations. Okay, that means rank of A minus lambda I is less than n. Okay, that means the rank of this matrix is less than n, and that basically implies that you know cannot. So, this implies that you cannot determine all x1, x2 etc. up to xn uniquely. So, there is no unique choice of these x1, x2 up to xn. Okay. In fact, typically what we do is we take one of them to some number and you express all of them in terms of that single coefficient. Okay. So, we will see an example of how to do this, but the point is you should keep in mind that whenever you have eigenvalues, okay, eigenvectors, you cannot determine the eigenvector uniquely. And there is another reason for this, and I will just mention this right here. Okay, it is fairly easy to see. I will also mention that you can solve for these eigenvector coefficients using row operations, okay, and we will see an example of that. But before that, I just want to mention that suppose we have Ax equal to lambda x, okay, and y equal to c times x, okay, y is a constant times x, okay, then ay is equal to, you can see easily this is a times cx, okay. Now c is just a scalar, so you can take it to the left of the matrix, and so I can write this as c times ax, and ax is nothing but lambda x. So I can write this as c times lambda x, or I can write this as lambda times cx, or I can write this as lambda times y. Okay. So what I have is that this implies that ay equal to lambda y. Okay. So what this implies is that if x is an eigenvector of A with eigenvalue lambda, then y equal to some constant times x is also an eigenvector of A, and it is not just it is an eigenvector of A with same eigenvalue lambda. Okay, so that means if you have an eigenvector, then you can just multiply it by a constant, you will get another eigenvector with the same eigenvalue. Okay, and that is why we say that eigenvectors cannot be determined uniquely by this procedure. Okay, so eigenvectors are not unique. You can take any eigenvector, multiply it by a scalar, you will get another eigenvector with the same eigenvalue. Okay, so now let's I'll just mention one thing before we take an example. So what is the significance of eigenvectors? Okay, so you can think of eigenvectors as important directions. Okay, important directions so what I can think of is, suppose I have a vector like this. Okay, so this is my vector, I am just showing it as an arrow. Okay, now when I operate it by this matrix A, okay, then I might get some other vector like this. Okay, that will in general it will point somewhere in some other direction, it might have a different length also, I will just show it expanded, it might look like this. Okay, so I operate this vector by this matrix A and I get something else. Okay, now you can do this for various vectors, and what you will find is that there are certain vectors, I will show this in this light blue color. So there are certain, I would say, directions, certain specific direction, any vector pointing in this direction will have the property that when I operate it on it by A, I will get another vector in the same direction, and maybe it is slightly longer or maybe slightly shorter, but whatever it is, they point in the same direction. So these two are in the same direction. Okay, so these two are in the same direction. So this is for eigenvectors. So eigenvectors have this property that when they are operated, so eigenvectors really represent some very specific directions. Okay, some very specific directions such that when the matrix operates on vectors in those pointing in those directions, it will give you another vector pointing in the same direction. Okay, and these are you can think of these as important directions of your system. Okay, so now let's take I'll just mention this briefly that your eigenvalues and eigenvectors, there is another way to think. You can think of your matrix as a representation of some physical quantity in some basis, and this will be an important theme that we will discuss when we are seeing applications of matrices in quantum mechanics. But first let us do an example. Let us do an example of an eigenvalue eigenvector calculation. And I will take a very simple example just to illustrate what you need to do in order to calculate eigenvalues and eigenvectors. So let me take a matrix A that looks like 1 0 0 1 2 minus 4 1, 2, 3, and I asked you to calculate the eigenvalues and eigenvectors of this. So, calculate eigenvalues and eigenvectors of this matrix. Okay. So, to calculate eigenvalues, so we use the secular equation which says that this determinant 1 minus lambda 0 0 1 2 minus lambda minus 4 1 2 3, this determinant has to be equal to 0. 3 minus lambda. Okay. Now what you can do is you can multiply this out. Now in this case you have the first row has just one non-zero element. So when I multiply this out, I will get 1 minus lambda times, I will get two terms, I will get 2 minus lambda into 3 minus lambda plus 2 into 4 is 8, and this has to be equal to 0. So, immediately you can see that lambda equal to 1 will satisfy this. So, one root of this cubic equation is lambda equal to 1. So, lambda equal to 1, or now if I just expand this out, I will get lambda square minus 5 lambda plus 14 equal to 0. Okay. So, and this implies lambda is equal to 5 plus minus. So, it will be 5 plus minus. So, what do you have? So, you have 5 square is so square root of 5 square is 25 minus. So, you have 14 into 4 is 56 divided by 2. Okay. So, this implies, so therefore, what you say is lambda equal to 1 or lambda equal to 5 plus root 31 times I is the unit imaginary number divided by 2, or lambda equal to 5 minus root 31 I divided by 2. So, these are the three roots of this secular equation, and these are the three eigenvalues. So, we have calculated the three eigenvalues. Now, what we need to do next is to calculate the eigenvectors. So, I will just take one example. Let us take lambda equal to 1. So, if we take lambda equal to 1, so I will calculate the eigenvector corresponding to lambda equal to 1. Okay. So, what I do is I take lambda equal to 1 and I put it in my equation. So, what I will get is my equation which is shown in over here. So, what I am going to do is I am going to put lambda equal to 1 in this in an equation of this form, and what I will get is the following equation. So, I will get 1 minus lambda. Now, lambda is 1. So, I get my equation 1 minus 1 is 0 0 0 1, 2 minus 1 is 1 minus 4 1 2 2. This times your eigenvalue or your eigenvector, I will just give it some coefficients x1, x2, x3, and this has to be equal to 0 0 0. Okay. And what you can do is you can take let us say for convenience we will take since I said now you have only two equations and you have three unknowns. So, you can choose one of the unknowns arbitrarily. So, let x3 equal to 1. Okay. So, then what you have is you have two equations, x1 plus x2 minus 4 equal to 0 and x1 plus 2x2 plus 2 equal to 0. Okay. And you can go ahead and you can just subtract these equations. So, what you will get is x2 equal to minus 6 and x1 equal to 10. So, my eigenvector corresponding to this is basically given by 10 minus 6 1. So, this is my eigenvector. Okay. So, notice what I had to do is I had to choose one of them arbitrarily. In this case I just chose x3 equal to 1. I could have also chosen x1 equal to 1 or x2 equal to 1, then I would have got appropriately I would have got all these other quantities scaled. Okay. So, basically my eigenvectors are proportional to this 10 minus 6 1. Okay. Okay. So, now before we conclude this lecture, I just want to say why eigenvalues and eigenvectors are very important, okay, in quantum mechanics. In quantum mechanics, the eigenvalue equation is has the following form. So, suppose you have an operator O, okay, and it operates on some state psi, okay, you get lambda times psi. Okay, then you say that and I will just put a subscript lambda, then you say that this is called an eigenfunction of the operator O, and this is called the eigenvalue. Okay. So, this is a typical eigenvalue equation that you write in quantum mechanics, and now if you are using a certain basis to represent your functions, then your state functions, they look like vectors, okay, and your operators look like matrices. Okay. So, so you can have operators in quantum mechanics represented as matrices in certain basis. Okay, this is a very important way to think about quantum mechanics. So, in fact, some of the earliest development of quantum mechanics were done using matrix algebra. Okay, and once you do that, then the significance of eigenvalues eigenvalues represent observed values, and eigenvectors. Okay, these are specific vectors or directions. Or in this case you can also think of them as functions. Okay. So, there is a very natural use of eigenvalues and eigenvectors in quantum mechanics. Okay.